On the other hand, the other thing that could happen is that actually the line is contained in the plane. And then, well, it means any point on that line will actually solve automatically the third equation. Okay, so if you try solving a system that looks like this by hand, what you will notice, if you do substitutions, eliminations, and so on, what you will notice is that, after you've dealt with two of the equations, the third one here would actually turn out to be the same as what you got out of the first two. It doesn't give you any additional information. It's as if you had only two equations. The previous case would be when actually the third equation contradicts something that you can get out of the first two. For example, maybe out of the first two you got x plus z equals 1, and the third equation is x plus z equals 2. Well, it can't be 1 and 2 at the same time. Maybe another way to say it is that this picture is one where you can get, out of the equations you get a number equals a different number. That's impossible. And that picture is one where out of the equations you get 0 equals 0, which is certainly true, but isn't a very useful equation. So you can't actually finish solving. Okay, so let me write that down. So unless the third plane, let's say it is parallel to the line where P1 and P2 intersect. So then there's two subcases. If the line of intersections of P1 and P2 is actually contained in P3, in the third plane, then we have infinitely many solutions. Namely, any point on the line will automatically solve the third equation. Now, the other possibility, the other subcase is if the line of intersection of P1 and P2 is parallel to P3 and not contained in it. Then we get no solutions. Okay, so again, just to show you the pictures once again, when we have the first two planes, they give us a line. And now, depending on what happens to that line in relation to the third plane, various situations can happen. So if the third line just hits, if a line hits the third plane in a point, then that's going to be our solution. And if that line instead is parallel to the third plane, well, if it's parallel and outside of it, then we have no solution. If it's parallel and contained in it, actually, then we have infinitely many solutions. Okay, so going back to our list of possibilities, that means, well, let's see what can happen. So no solution, well, we've seen that happens when the line where the first two planes intersect is parallel to the third one. That exists. 2 points, well, that didn't come up. Okay, and as I said, the problem is if the line of intersection of the first two planes actually has 2 points that are in the third plane, well, then that means actually the entire line must also be in the third plane. So If you have two solutions, then you have more than two, actually. In fact, you have infinitely many, and we've seen that can happen. Okay, tetrahedron still doesn't look very promising. What about a plane? Well, that's a case that I didn't explain because I've been assuming that P1 and P2 are different planes and they intersect in a line. But in fact, well, they could be parallel, in which case we already have no solution to the first two equations, or they could be the same plane. And now if a third plane is also the same plane, if all three planes are the same plane, well, then you have a plane of solutions. If I give you 3 times the same equation, that is a linear system. It's not a very interesting one, but it is a linear system. Okay, and I don't know is no longer a solution either. Okay, any questions? Yes?
What's the geometric significance of x plus y plus z is equal to 1 as opposed to 2 or 3?
Okay, so that's a very good question. The question is, what is the geometric significance of an equation like x plus y plus z, or say this one equals to 1, 2, 3, or something else? Well, if the equation is x plus y plus z equals 0, it means that our plane is passing through the origin. And then if we change the constant, it means we move to a parallel plane. So the first guess that you might have is that this number on the right-hand side is the distance between the origin and the plane. It tells us how far from the origin we are. That is not quite true. In fact, that would be true if the coefficients here form the unit vector. Then this guy would just be the distance to the origin. Otherwise, you have to actually scale by the length of this normal vector. And I think there's a problem in the notes that will show you exactly how this works. Okay? But you should think of it roughly as how much have we moved the plane away from the origin. That's the meaning of this last term, d, that's in the right-hand side of the equation. Okay. So let's try to think about what exactly this case, how do we detect now in which situation we are? Because that's all very nice in the picture, but it's difficult to draw planes. In fact, when I draw these pictures, I'm always very careful not to actually try to pretend to draw an actual plane given by an equation, or when I do, then it's blatantly false. It's difficult to draw a plane correctly. So instead, let's try to think about it in terms of matrices. In particular, what's wrong with this? Why can't we always say the solution is x equals A inverse B?